All right, here we go. So today's video, 3.2, we're going to be learning about 2 and 3-dimensional motion. All right. So everything we've done so far this year has been 1-dimensional motion, where pretty much everything has occurred just along, one straight line. We've usually called it the x-axis, right? Okay. Well, last year in honors we did projectiles, right? And one of the things we learned was that when you have a projectile, it's got motion both along the x-axis and along the y-axis, right? And so we need to find a way to distinguish between those two, right? And so we're going to use the notation that we learned the other day. So the idea is, suppose the projectile is right here, for example, all right? Well, at that point, it's going to have some, x position. It's going to have some y position, all right? The overall position, we're going to use the letter r as a vector to represent position, all right? And so at this point, we would say, okay, well, the projectile has a position of x in the I direction and y in the j direction, okay? And if we ever do 3-dimensional motion, which I really don't think will come up, we always use k to indicate the z direction, okay? But basically, for our purposes, we're just going to be dealing with this, okay? So basically what this is going to boil down to is we're basically going to be doing last chapter again, but this time, instead of just having to think about velocity or acceleration in 1 dimension, we'll have to think about velocity and acceleration in 2 dimensions. Okay? So, position, anytime you're dealing with multiple dimensions, the position vector, instead of using x or y, we're going to use r. Okay? So, similarly, if we ever have displacement, same idea. Okay? Your displacement can be thought of in components, so our change in position, our displacement is now change in r instead of change in x, and then that has components, x, y, and occasionally z, but not usually for our purposes. Okay? All right, so probably the easiest thing here to do would be to do an example. All right? So something you might not know about me is I'm actually a relatively good pogo sticker, but I need a new one. So I just ordered a new one, right? And so it's coming from Amazon right now. All right, so let's consider the Amazon warehouse the origin. Okay, so that's, in other words, at a coordinate of 0, 0. All right, we're going to measure our time in hours. I'm going to apologize in advance. Anytime I say seconds in this example, I mean hours. All right, and so the idea then is the position of the drone is going to be given in 2 parts. All right, so this expression here represents the x position of the drone. So if I want to find out how far east or west of the warehouse the drone is at any time, I just plug in my, the number of hours in here for t and plug it into the equation, okay? And similarly, the drone is also going to go north and south, all right? And so this expression here, gives us how far north or south of the warehouse the drone is at any given instant, okay? So you can see, we could plug in values of t for x. So if you plug in 0 for x, if you plug in 0, for your time, then your x turns out to be 0, okay? If you plug in 0.2, it gives you, some other value, all right? Similarly, we could go through and we could plug in values for y. We could plug in 0. If you plug in 0 for t, you can see we get 0. If you plug in 0.2 hours, you're going to get, some other value, etc. And we could go through and we could fill in this whole chart, right? All the way up to a total of 4 hours, okay? So you can do that if you want. Tedious. I don't know that there's a lot of value in it. Basically, it's plug and chuck, right? So you can see on the next slide here, I've got all of the answers here, okay? So that's the deal. So what this chart gives us is, for different times, the x and y position of the drone, right? Now, so how do we deal with this information? Well, there's a couple things we could do. Option 1 is we could, if we wanted to, we could take this and make, a position versus time graph, right? Where we graph time on the x-axis and x on the y-axis, right? And then we could graph this guy, right? But remember, regardless, time is your independent variable, right? And then x and y are your dependent variables, okay? So we could graph both of these polynomials here, right? We could graph x as a function of time, and we could graph y as a function of time, right? And if you did that, it would look like this, okay? So here's our x function, here's our y function, okay? And so what does it tell us? Well, it tells us that let's see, it looks like after a little less than half an hour, our drone has, let's see, so it's moving, well, our X position is decreasing, right? So it's moving west, stops moving west, begins moving east, moves east, moves east, moves east, moves east, slows down, stops, and then it goes back west, 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 faster and faster and faster and faster, right? And similarly, in the Y direction, it begins moving north, but then it slows down, stops moving north, begins going south, faster and faster and faster, stops moving south, goes back north again, right? Okay. Sorry, my hands are a little shaky here. Coffee. Okay, so we could do this, but the problem is it's sort of tough to visualize the path that this thing is following, right? I mean, I can tell that, you know, at the beginning it's going, what did we decide? West at the beginning and north at the beginning. So it looks like at the beginning it's kind of going northwest, right? And, you know, as it goes, the path changes, right? So let's think about this another way. Another way we could do this is this. Look at this. So what we've got here is a whole bunch of xy coordinates, right? So at time 0, that's an xy coordinate. My position is 0, 0. After 0.2 hours, my position is that, negative 0.67 in the x direction and 2.74 in the y direction. So we've got all of these xy coordinates, right? And they're spaced out by a difference of 0.2 hours, right? So I could, if I wanted to, I could just plot all of these xy coordinates, right? So if you do that, here's what we get. So if you do that, you get this pattern that I've got over here, okay? So we're starting at a position of 0, 0, and then around like this, right? Okay, and each dot represents 0.2 hours, right? Well, they're 0.2 hours apart, I guess would be the better way to say that, right? So this is at t equals 0, t equals 0.2, 0.4, 0.6, 0.8. So this looks like it's 1 hour. So does that make sense? Let's see. Oh yeah, after 1 hour, our x position is 0 and our y is that, okay? So 1.2, 1.4, 1.6, 1.8, here's t equals 2, 2, 4, 6, 8, t equals 3, etc., right? Okay, so what this actually represents is the path that the drone follows, right? But what I want you to notice is that neither of my axes here are time, right? My two axes are, like, this is an actual, like, map, right? Like, here's the Amazon warehouse, and here it is driving, you know, northwest, and it follows this path, right? Now, suppose I wanted to know something about the direction that it's traveled. Well, at any given instant, the direction that the drone is traveling is tangent to the curve. Okay, so right here, the drone is going this way. Okay, over here, the drone is going straight south, right? Let's check that. That's at 2.2 hours, right? Oh, I can't do that yet. We'll do that later. Okay, but so the tangent line points in the direction of the velocity, but it doesn't tell us anything about how fast it's moving. In order to determine how fast it's moving, well, pause the video and see if you can figure it out. Not numerically, but just relatively how fast it's going. Okay, so here's what I know. I know that in the first 0.2 hours, it went this far. In the next 0.2 hours, it only went this far. In the next 0.2 hours, it only went this far, right? So when is it going fastest? Oh, at the beginning, right? Overall, for the whole trip, where is it going fastest? Probably over here, right? Because that's where it looks like it made the most advancement, the largest displacement in the same 0.2 hours, right? Okay, so that is that. All right, so now let's talk a little bit more about that, about the idea of velocity. All right, well, in the same way that we keep track of position and displacement in terms of our x and y components, the I and j parts, we're going to do the same thing with velocity, okay? And so what we have then is this. So average velocity is change in position divided by time, okay? So it's exactly the same thing as we learned before, all right? A simple example, this actually has nothing to do with the drone example, but I just want to point something out. So suppose you've got an object that has a displacement of 0.2 miles in the x direction and 3 miles in the z direction, actually, here, right? It doesn't really matter, but whatever. So there's our displacement vector, right? We got 12 miles along one axis and 3 miles on another axis, okay? Oh, I guess those are meters, right? Okay? So if that takes 2 seconds, then here's our, let me switch to highlighter here. So here's our displacement vector. Here's our time, right? Okay, so when you divide, you just divide component-wise, okay? Okay, so 12 divided by 2 gives us the 6, and then 3 divided by 2 gives us the 1.5. Okay, so that's how you find your average velocity, all right? So instantaneous velocity is just the derivative, okay? And again, you just take the derivative component-wise, okay? So probably easiest to just dive in and do an example. I'm going to skip this. Maybe we'll come back to it if there's time. It's not that super important. Okay, so so where were we at? So we knew that we had these two. Whoa, why is that there? So we knew we had these two things, right? So here's our x, right? So to find the velocity in the x direction, I simply take the derivative, right? So my velocity in the x direction is the derivative of x with respect to time, right? So just take the derivative. So you're going to go 3 times negative 1.5 gives you negative 4.5. Reduce the exponent. Plus 2 times 6 is 12. Reduce the exponent. Minus 4.5, right? Okay, and similarly, I can find the vertical velocity, right? That's going to be the derivative of the y component with respect to time. For some reason this pen, sorry. Okay, so take the derivative. So 3t, sorry, 3 times 2 is 6t, reduce the exponent, minus 24t plus 16, right? Okay. So if I wanted to, I could find the velocity after 2 hours, right? So let's do that over here. So the velocity after 2 hours would be the velocity in the x direction after 2 hours in the I direction plus the velocity in the y direction after 2 hours, right? You can put a little j there, right? So let's do that. Let's find v of 2. Or sorry, vx of 2. So if I plug 2 in for each of these times, then I get, where did I put my notes? All right, here we go. So the velocity after 2 hours ends up being, oops. Oh no, oh my god. So that ends up being 1.5 meters per second. All right, and similarly, if you find Vy after 2 hours by just plugging in your, 2 for your time, then you end up getting negative 8 meters a second. So the velocity after 2 hours then is 1.5 I minus 8. That's an 8 pen, this pen, J, and then it's all meters per second. Okay. Now, to find the average velocity in the first 2 hours, that's a different deal, right? So V average is change in R over T. So what's our change in R? Well, that's change in X in the I direction plus change in Y in the J direction divided by our time, which is 2 hours, right? So to find our change in X and our change in Y, let's go back to the chart. Okay, so our change in X in the Y direction, our change in X and our displacement in the X direction, let's go to 3. So our change in X is 3, right? And similarly, our change in Y, we went from 0 to 0. So our change in Y is 0, right? So So now we can just plug those in over here. Oh, well, actually, let me... yeah, I guess that's... Well, here's what I was going to say. What that shows us is in those 2 hours, look, all of our displacement was to the, what, to the east, right? Because here's where we were after 2 hours, right? So our average velocity is just going to have an x component. So I think all I need to worry about is the I, right? Because we just showed that our y component was 0. Okay, so here we go. So our V average, then our change in x was 3 over 2, so that's 1.5 I meters per second. All right, so now, what if we want to talk about acceleration? Here's where things get a little more involved. All right, so acceleration is, again, it's exactly what you'd think it is. If you're talking about average acceleration, you just find your change in velocity and divide it by your time. And to find your instantaneous acceleration, it's just taking another derivative, okay? This is basically more of the same thing. All right, so let's do another example here. Okay, so where we're at was this. So we're trying to find the acceleration after 2 hours. So a minute ago, we found this Vx and this Vy. So to find the acceleration, let's go over here where we got a little bit of space. So our acceleration in the x direction should be the derivative of Vx with respect to time, right? So take another derivative. So let's see, negative 4.5 times 2 is negative 9t plus 12. And similarly, our acceleration in the y direction is the derivative of Vy with respect to time. And so that gives us, what, 12t minus 24, right? So to find the acceleration after 2 hours, you just plug in your numbers, right? So our acceleration after 2 hours is, well, if I plug 2 in here, I'm going to get negative 18 plus 12 is negative 6 in the x direction. And if I plug in 2 here, I'm going to get 0, right? So there's my answer. All right? Now to find the average acceleration is a little bit more work, all right? So I don't know that I'm going to go through it because it's just kind of tedious, but so to find our A average, we want the velocity after 2 hours, which we just found a minute ago, minus the velocity after 0 hours divided by 2 hours, right? So let's see, I guess we can do this, right? So the velocity after 2 hours we had found a minute ago. So the velocity after 2 hours was 1.5 I minus 8j minus the velocity after 0 hours. Well, let's see. The x, if you plug in Vx of 0, you're just going to get negative 4.5, and Vy of 0 is going to give you 16. So down here I'm going to go, let's see, negative 4.5 I plus 16j all over 2. Okay? So now we just got to subtract this all out, right? So we're going to do it component-wise. So we've got 1.5i minus negative 4.5i. That's the same as plus 4.5. So we're going to get 6i. And then negative 8 minus... Oh, shoot, I made a mistake here. This was supposed to be plus 16, right? I just made a little change there. This was supposed to be plus 16. All right, so minus 16. So negative 8 minus 16 is what? Minus 24? Jive? You can't correct me if I'm making a mistake, so we're just going to move ahead. So minus 24j, right? And then all divided by 2, right? So we're going to end up with 3i minus 12j meters per second squared. All right, so that's how that works. Is that everything? Let's see, what else we got? Oh, right, okay, so let's see if we can tie this all together in one example. Okay, and this is the last one. Okay, so here we've got a bird with a jetpack, all right? And here's what it tells us. It tells us that the bird has an initial velocity of 5I minus 2J meters per second, okay? If it instantly switches on the jetpack, all right? Gotcha. Oh, here, this is supposed to say that the XY represents east-west. Okay, anyway. Oh, I don't know what this even means. Don't worry about that. We're talking about compass directions, right? East, west, north, south. Okay, so it says, unfortunately, the jetpack is on crooked, so it gives him a constant acceleration, but the acceleration is 30 degrees west of north. Holy cow, you guys. I just put south and north in the opposite direction, didn't I? Let's try this one more time. North, south. There we go. All right. So the acceleration that he's given, let me do the acceleration in blue. The acceleration he's given is this way. Okay. So that has components, right? So let's see. 4 meters per second squared. Here's north. This is the 30 degrees. Here's west. So if you do a little bit of trig, what we'll find is that our acceleration in the y direction is 3.46 meters a second squared, and our acceleration in the x direction is negative 2 meters a second squared. So our overall acceleration is negative 2I plus 3.46 meters per second squared. Okay? Now, we want to find the, here it asks for the instantaneous velocity at the end is 3 seconds. Well, look, we've got a constant acceleration, so we can use our kinematics equations. Okay, so there's that stupid thing again. So here we go. So remember this equation from forever ago? Vf equals Vi plus At. Right? So our Vi is 5I minus 2J plus our acceleration is negative 2I plus 3.46. Damn, this pen always does this. About 15 minutes into these videos, it starts pooping out. J, and then times 3. Okay, so solve it. Well, let's see. So I guess the first thing we want to do is distribute this 3 here. Okay, so we're going to get 5I minus 2J minus 6I. What's the purple? Let me try changing colors. 5I minus 2. Nope. All right, well, we're going to muscle through because the video is almost done. So, all these stupid spots. All right, so, and then 3 times 4.6 gives us a number that I've written down. These videos are... All right, so that gives you 10.4 basically. So plus 10.4 J. So now you just simplify, right? So 5I minus 6I is negative 1I plus 8.4J. This is a J. Okay? All right, and then finally, to find the average velocity, well, the only way to find average velocity is to do displacement divided by time. No, that is not true. That is one of the ways to do it. So option 1 is find your x and y displacement and divide by the time. Again, just using kinematics equations. An easier way, our acceleration is constant, right? So here is our Vi. Here is our Vf. So we can just do V average is Vf plus Vi over 2. Okay? So if we add these guys, let's see, 5I minus 1I right? Because we're just adding, right? So 5i plus negative 1i, so that gives us 4i. And then negative 2j plus 8.4j is 6.4j. Man, this pen. All right, and then divided by 2. Okay? And so you get 2i plus 3.2j. And I will see if I can solve this pen problem. Okay, so there we go. There's our average velocity. Oh, I forgot my units on both of these. Meters per second here, meters per second there. All right, there we go.